This lesson is for Unit 6, Lesson 1, and this unit is all about radical functions. And it's not just going to be about square roots. We're going to incorporate cube roots, fourth roots, not just with numbers, constants, but also with variables. Okay, so, and this is a really big thing to understand if you're going to move on to pre-calc next year or anytime in your future. So it's really good to understand how these concepts work. Okay, to start off, we are going to review what our perfect squares, perfect cubes, and perfect fourths are. Again, these are raised to these powers. And if you're in class, we will make a note card for you to keep handy because all these numbers come in to be very useful as we're breaking down and simplifying our radicals. To start off, let's start off with our perfect squares. We know that 1 squared is 1, 2 squared is 4, 3 squared is 9. Then we have 4 squared for 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 is 121, and 12 squared is 144. And we could keep going. I'm out of room. Hey, those are perfect squares. We've done a lot of factoring with squares, difference of squares, so I feel like that's a little bit more familiar to us. We kind of started doing more with cubes as well. So our perfect cubes are 1 cubed is still 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, 6 cubed is 216, 7 cubed is 343, 8 cubed is 512, 9 cubed is 729, and 10 cubed is 1,000. And again, it could keep going. And then our perfect fourths. These really will probably feel new and not as familiar, but we're going to start doing, again, fourth roots, so we need to know what our fourth powers are. So 1 to the 4th power, that's what we're doing here. 1 to the 4th is 1, 2 to the 4th is 2 times itself, 4 times is 16, and then 3 to the 4th is 81. 4 to the 4th is 256, 5 to the 4th is 625, 6 to the 4th is 1296. Notice our numbers get really big a lot faster because when you multiply things by themselves more times, again, it's going to make a lot bigger number faster. 7 to the 4th power is 2401, 8 to the 4th is 4096, and they go on and on. All right, we're going to use those parts when we simplify our radicals. So let's go over and label our parts of a radical. It says the nth root, okay, nth just means any type of root we are looking for. We could put a number in for n. Of a real number, we're working with real numbers right now, no imaginaries, can be written as the radical expression, the nth root of a. So this number that goes in for n, that is called the index. And a lot of times we are used to not seeing a number on the outside of the radical, the index. And that's down here. It says if there is no index, assume that it is 2, or n equals 2, which means it's a square root. All right, so we don't have to put the 2, it's implied. Just like with variables, if it doesn't have a coefficient, it's a coefficient of 1 or an exponent of 1. For square roots, it's implied that it's an index of 2. The little house is actually called a radical, okay? And then the number underneath the radical has a name too. It's called a radicand. Okay, and we'll be using those words frequently, and hopefully you'll get used to them. Okay, this part is saying to give all possible roots to the radicals below, all possible roots. So we have the square root of 16. Remember, it's a square root if there's no number outside the radical. And we're asking, what's the square root of 16? And it's saying all possible. We know the square root of 16 is 4 because if we undo that, or work the other way, 4 squared equals positive 16. But it could also be negative 4, because if we put negative 4 in parentheses and square it, that means negative 4 times negative 4, which also equals positive 16. So the answer here, number of roots, we would say it is plus or minus 4, positive and negative 4. So when we are taking the square root, when we're asking for all possible roots, it could be a positive or negative of that value when we're dealing with square roots, because there's two negatives multiplied to a positive and two positives multiplied to a positive. So the square root of 121, we would say that could be positive and negative 11. And then the square root of 289, that is 17 times 17. Again, to take the square root, hopefully we remember this as well. Square root is what two identical numbers were multiplied to make the radicand. So this is plus or minus 17. And we can even take the square root of fractions. Remember, we take the square root of the numerator. The square root of 4 is 2. The square root of the denominator, 25, is 5. So we put a plus or minus sign in front, and the square root of 4/25 is positive or negative 2/5. Okay. Our next few examples, we have now the cube root of 8. And now that means because we have this 3 right here, we're wanting to know what number times its own self 3 times made the radicand number 8. And that is 2 times 2 times 2, 3 matching numbers, so it is just 2. Now, it is positive only, okay? If 3 positives multiply to make a positive, if I did negative 2 times negative 2 times negative 2, that would equal negative 8. So that doesn't work. We can't say plus or minus 2 when we do cube roots. If we have a positive radicand, our answer is positive. If we have a negative radicand, our answer will be negative. Okay, because we have an odd amount of numbers, and so the odds don't all cancel out with a sign. Okay, the cube root of 343 is just going to be positive 7. These are all perfect roots that we are working with right now. The cube root of negative 125, again, this would be negative 5 times negative 5 times negative 5. 3 identical numbers, and they have to be identical, their signs and all, so that makes the answer just negative 5. Those are the 3 numbers that multiplied, matching numbers that multiply to make negative 125. And then the cube root of negative 1 over 27, again, it works the same way. The cube root of 1, negative 1 is 1, and it's always that the negative applies to the numerator, not the denominator. The cube root of 27 is 3, so it's negative 1/3. Again, cube roots always keep the sign of the radicand. Okay, and our last little bit, fourth roots, and these are all perfect fourths. Okay, what is the fourth root of positive 1? All possible roots again. So this could be 1 times 1 times 1 times 1, because fourth root means I need 4 identical numbers. That equals 1. But what about negative 1 times negative 1 times negative 1 times negative 1? If I multiply 4 negative numbers, remember 2 negatives cancel to make a positive. These 2 would cancel to make a positive. So that also equals 1. So we're back to having an even index means that we do plus or minus that value, plus or minus 1. So odds, just keep the sign. Even indexes, we're plus or minus. The fourth root of 2,401 would be plus or minus 7. The fourth root of 4096 is plus or minus 8. And again, you could do this all on your calculator. The fourth root of 81 over 16 is plus or minus 3/2. All right, again, this section, these were all perfect squares, cubes, and fourths. But now we're going to learn what you do if you don't have perfect squares, cubes, and fourths. We have to still simplify radicals. It's a lot like simplifying fractions, a little bit more complicated, but everything in algebra has to be simplified. It's just kind of a universal rule. So we'll get into that in the next slide. All right, before we start simplifying our radicals, we'll go over this little chart to help us simplify our radicals. If we have an even index, okay, like it's a square root, fourth root, sixth root, and so on, and the number underneath that radicand is positive, we will get real answers, and we will get 2. They will be positive and negative. Just like the square root of 64 is plus or minus 8, because 8 squared is 64, and negative 8 squared is 64. If we have an odd index, like a cube root or a fifth root, and the number underneath the radical, that radicand, is positive, we will still have real roots. We can take the cube root of negatives without getting imaginary numbers, but we just get one root that will also be positive. Okay. If the index is odd still, so this is like a cube root that we're talking about, but the number underneath is negative, we'll still get a real answer, but it will only be one answer that is negative. I think above when I said how it was in red, yeah. Anytime we root a positive number, we're going to get a real number. But we can root a cube root or fifth root an odd number that's negative and still get a real number. We just keep the sign like we showed before. And then last, if our index is even, okay, back to square root or fourth root, but the number underneath is negative, we are getting imaginary roots. And we'll have two imaginary roots that will be plus or minus. All right. Okay, so this next part of the lesson can be a little tricky to teach because all of you know that your Casios will simplify square roots, those types of radicals, and so you just want to type in the square root of 117 and go straight to your answer, which I understand, but you do need to understand the process behind it because your calculator will not simplify non-perfect cube roots or fourth roots. So it's the same principles, and it also does not simplify variables. So we are going to just hopefully go over this the long way. Your calculator is a way to check your answer and to do it when we're like in a rush, but you do need to understand these algebraic principles. So I need to simplify the square root of 117. It is not a perfect square. Now the concept with simplifying these is that there is a factor. It's a number that multiplies with another number to make 117 that is a perfect square, and we can square root that part. So we have like a rule of thumb, and over here in red I've written down a list of some perfect squares. Our rule of thumb is the factor of 117 that's a perfect square cannot be more than half of 117. So I start by doing like that number and I divide it by 2 and I get 58.5. And really that's just a starting point on my list. It helps me narrow down and so I don't have to check every factor or perfect square. And so 58 fits in between 49 and 64. So I'm going to start, okay, this is just where I start. And again, I'm using this list in red because these numbers are perfect squares, okay, and these are the only numbers that we can take the square root of evenly. So I'm using this list. And so I start and I say 117 divided by 49, and that gives me a decimal. So I'm like, okay, it's not a factor, right? It has to divide to a whole number to be a factor. And then I cross it off my list. 117 divided by 36, decimal or fraction, so not a factor. 117 divided by 25 is a decimal. Then 16, and I know it's kind of annoying, but it's just the process that we have to go through. And then I say, get to 117 divided by 9. And 117 divided by 9 is 13. Okay, so these are the two numbers I want to use to simplify this radical. I could say that 117 is the same thing as 9 times 13. I didn't change its value. I'm writing it in a different way, and you know we do that a lot in algebra. But I like this because I can take the square root of 9. When we take the square root of a number, okay, that number that is the square root comes outside the radical. So I kind of draw it like this. I cross off that 9, and a 3 comes out because the square root of 9 is 3. So that leaves my answer as 3. The 13 had to stay inside because he's not a perfect square. We just kind of reject him, leave the non-perfect factor inside the radical, and this is done. Okay, now number 2, we're saying 4 times the square root of 320. We need to simplify this 320. Okay, we want to know what factor of 320, the biggest factor also, that is a perfect square. So I start off and I'm going to say 320 divided by 2. And that is 160. So that gives me a starting point. I had a little bit bigger list here. So it has to be 160 or 144 or below because that just gave me a starting point. So again, I just start here at 144 and we just use our calculator and I do 320 divided by 144 and that's a decimal. And I keep working my way down. 320 divided by 121. Obviously not 100 or 81. And then finally I get to 64 because I have to start high numbers and work my way down so we find the biggest factor. It's like not simplifying a fraction of like 10 over 20 to only 5/10 if we didn't simplify it all the way, right? Fully simplifying 10 over 20 is 1/2. So we want to find that biggest factor first. 64 times 5 is 320. So again, I'm going to bring down this 4. 4 is getting multiplied to whatever comes out of here. It's 4, and then we have square root. I'm going to change 320 to be the same thing as 64 times 5. And then I'm like, okay, I like this 64. The square root of 64, this comes out as an 8, but there's already another number out here, 4. So they get multiplied. Okay, 4 times 8 is 32, and the 5 stayed underneath. So the answer is 32 square root 5. Okay, now in number 3, we've got 2 times the cube root of 348. Now we're dealing with a cube root, so I'm using my perfect cubes now, okay? Now only these numbers over here, one that I wrote down on this list, can be taken a cube root of perfectly. So we have to use numbers from our perfect cubes list when we are doing cube roots. So 48 is not a perfect cube, but there is a factor, a number that multiplies to 48 from our perfect cubes list. That is, and we will take the cube root of that part and multiply it to 2. So again, my process is kind of the same. I'm going to divide 48 in half, and half of 48 is 24. Okay, so I like this. It kind of narrows my list down a little bit better. So I do 48 divided by 27. Oh, I even went too high. 48 divided by 8 is 6. So we know it's 8 times 6. So I'll write this as the 2 comes down, and I'm going to say it's the cube root of 8 times 6. And I like this because, again, the cube root of 8 is 2. There's already a 2 on the outside, so the 2 2's get multiplied. 2 times 2 is 4. And we have to make sure you put the little 3, that index, that cube root, on the outside, and then put 6, especially when you do Excel, or it won't be correct. So if you're missing things on Excel, check to make sure you have the right index on the outside. Okay, number 4. I have 3 times the cube root of 108. So I'm going to take half of 100. I know that's like 50 something, so I'm about between 27 and 64. So I start 108. This is again my starting point. 108 divided by 27 is 4. Okay, so 27 times 4 make 108. So we rewrite it as 3 and then cube root of 27. And I like to put my perfect number first, times 4. And then I take the cube root of the perfect part, the number from my list. The cube root of 27 is 3. It gets multiplied to the 3 that's already out there. 3 times 3 is 9. And we keep the cube root, that non-perfect cubed, inside the radical. Okay, number 5, we have the cube root of negative 250. Remember, we can take the cube roots of negatives without getting an imaginary number. It's just important to break down the negative part correctly. So if I take half of 250, I actually get a number on the list. I get 125. So that's great. If you divide something in half and you get a number on the list, you've already found the number you are looking for. So I'm going to break it down like this. The cube root of a negative 250, we're going to say that was 125 times 3. Sorry, 125 times 2. My brain's a little scattered today. Now, where does the negative go? It always goes with the part that was on the list. We'll say negative 125 times positive 2. You never leave the negative underneath the radical. It always has to come out. So we say the cube root of negative 125 is negative 5. Okay, do not leave the negative underneath the radical. So this is just negative 5 on the outside now, cube root of positive 2. Okay, radicands, always positive in your answer. Pull the negatives out. That's a big rule. Okay, so number 6, we have 6 times the cube root of negative 2. Well, look at this. Negative 2, like half of that is 1. Oh, great. You can't, like there's not another factor really that's a cube root of negative 2. A lot of times we don't even deal with the ones, but I cannot leave the negative underneath the radical. That is like the big no-no here. So what I'm going to do is say this is 6 cube root of -1, right? It's on the list, times +2, because I have to make sure that the radicand is positive in my final answer. The cube root of -1 is just -1. It multiplies to the 6 that's already out there. So we have -6 cube root of +2. Again, because radicands always have to be positive in our final answer. Okay, now on 7 and 8, we are fourth rooting some radicals. And so again, that means what number times its own self? 4 times was a factor of these. Always pay attention to what your index is so you know which list to use. So I take my 162 and I divide it by 2 and I get 81. Again, that's great because I got a number on my list. So 81 times 2 makes 162. So we'll rewrite this as 3, and then we have the fourth root of 81 times 2. Okay, the part I like is the 81. There is a fourth root of 81. That fourth root is 3. So that 3 comes out. So there's already a 3. Wow, what was that? There was already a 3 on the outside. So we have the 3 times 3, and then the fourth root of 2. 3 times 3 is 9. So 9, fourth root 2 is our answer. Okay, number 8, we have 5 times the fourth root of 2,592. And half of 2,592 is 1,296. Okay, so we already have our perfect fourth again. That was a little too easy, if you ask me. So I'll write this as 5 fourth root of 1,296 times 2. I take the fourth root of the number that's from my list. That's the perfect part. The fourth root of 1,296 is 6. So that 6 comes out. It has to multiply with the 5 that's already on the outside. Don't forget to do that. 6 times 5 is 30. And then we put fourth root 2 as our leftover part. Okay, now in examples 9 through 18, we're going to simplify radicals with variables, with letters now, because this is algebra. We always like to throw those letters in. Now, we have like our exponent rules when we're rooting exponents. The number part will be done exactly the same with the coefficients. But for exponents, if we're doing a square root, okay, you take the square root of an exponent by dividing them by 2. So we're looking for multiples of 2. Anything that is even, in other words, okay? That means it's a perfect square. We have to get rid of the part that makes it odd, and we'll go over that. Cube roots, we divide by 3. So exponents must be multiples of 3 to take cube roots. You are always dividing by the index when you root. So fourth roots, we must have multiples of 4. We divide by 4. Cube roots divide by 3, and square roots divide by 2. All right, so if it does not, we get rid of just like the extra part that doesn't let us divide evenly. So here we go. Number 9. I need to make my list. Let me put it on here. Okay, now when it comes to using variables and exponents, I kind of show it just a little bit differently. I'm going to make 2 houses. Okay, 32 is not a perfect square. My first house is for my perfect squares. Okay, I'll put perfect. And this is for my non-perfects. So 32 is not a perfect square. What's the factor of 32 that is? That process is the same. I take 32 and I divide it by 2 and I get 16. Okay, so I already have it. I put the perfect part, 16, in my house. I put the non-perfect part, the 2, that was the other factor, in my second house. Now remember, variables are perfect squares if they have even exponents. So 4 is a perfect square. So I put that whole thing inside my first radical. Now y to the 9th is not a perfect square, but I want the biggest part of 9 that I can square root. So when you're doing square roots, okay, you only have to say -1. Okay, because 9 minus 1 equals 8, which is a perfect square. So I'm going to put y8, or 8y's in other words, in my first house, and I had 1 left over, so it goes in the second house. It was the part that we needed to get rid of, okay, just like 2 was the factor that wasn't a perfect square to go in the second radical. Okay, that's all the leftover part that we cannot square root evenly. And then I go back to my first house and I'm square rooting all of this. The square root of 16 is 4. Okay, x is to the 4th power. When I square root it, I divide it by 2. 4 divided by 2 is 2. For y, I take 8 and divide it by 2, which is 4. Now that's everything that came out of the house because it was the perfect square part. And I leave 2y underneath. That was all the part that was not a perfect square. And this is my simplified answer. Okay, let's practice that some more. Now number 10, we have the square root of 324, a cubed, b7. So I'm going to start by making my 2 houses. And again, my first house is for my perfect part. Now 324, I didn't make my list big enough, but 324 is actually a perfect square. So I'm going to put that whole thing inside my first house. I don't need any numbers to go into my second house. Okay, now my a's. Okay, I have a cubed. 3 does not divide evenly by 2, but if I kick out one a, and so I put it in that second house, I'm left with, I just had a minus 1, a squared. And 2 is a perfect square, so it gets to go in the first house. 7 is not a perfect square either, so I'm going to kick out 1. Okay, I kick out 1 and I put it in the second house, and I'm left with 6 in the first house. And I like it because now everything in this first house is a perfect square. So the square root of 324 is 18. Notice there's no radical on it because we're taking it out of the house when we root it. For a, we do 2 divided by 2 is 1. So 1a comes out. And then for b, 6 divided by 2 is 3. So 3 b's come out. And we leave that leftover part of ab inside the radical. Okay, on number 11, I've got the cube root of 216 m cubed n to the 6th. Now you look at this number, 216 is on the list, so it is a perfect cube already. My variables exponents are 3 and 6, which are both divisible by 3, which is what they need to be because we're cube rooting them. So we divide the exponents by 3 to do that. Because this is all a perfect cube already, I do not need 2 houses. I'm just going to root it. The cube root of 216 is 6. Okay, for m cubed, we cube root that one by dividing by 3. 3 divided by 3 is 1, so 1m comes out. For n, we do 6 divided by 3 is 2, so 2 n's come out, leaving our answer as 6mn squared. All right, number 12, the cube root of 56, r to the 8th, s to the 4th. So I'm going to make, because 56 is not a perfect cube, I know I need 2 houses for sure. So 2 cube root houses, look at my little 3's. Okay, they have to be perfect cubes or divisible by 3 to come out. So I start, half of 56 gives me 20 something. So I'm down here. 56 does not divide by 27, but it does divide by 8. It's 8 times 7. So 8 gets to go in the first house, 7 in the second. Again, my first house is always for my perfect part, the part we can root. Now, r to the 8th. 8 does not divide by 3. 7, I keep working my way down. Okay, what number, the next highest number after 8 that does divide by 3? So not 7, but 6 does. So to get from 8 to 6, we kick out 2 r's. So I put that in the second house, my reject house. And then I keep r6 in the first. That's the part we can root. Then s's, 4 also does not divide by 3. So we kick out 1. 4 minus 1 is 3. 3 is divisible by 3. So we kicked out, remember, 1s, leaving us with 3. And then we root that first house. The cube root of 8 is 2. For r, we now have 6 divided by 3 that works, and that is by 3 is 2. And for s, 3 divided by 3 is 1. So 2r squared s is what comes out of our cube root, and we leave our little reject part as cube root of 7r squared s. So on 13, we have the cube root of negative 64 x to the 10th, y to the 21st. So we need multiples of 3 for our exponents, and I'm using my perfect cubes list. Now 64 is on my perfect cubes list, but notice we're taking the cube root of a negative, so I still need to break apart these numbers. So I'm going to make 2 cube root houses, and I'm going to say the negative part is the part we want to take out, the negative. So negative 64 times positive 1. And then for x to the 10th, again, 10 does not divide by 3. So if I say minus 1, I get to 9. 9 is divisible by 3, so we want to keep 9 in the first house, and we kicked out 1 to make that happen. Again, I'm always adding back to the original. 9 and 1 make 10. I didn't change value, I'm just rearranging. For y, 21 does divide by 3, so we're going to put that whole thing in the first house because it is perfect. It is divisible by 3. So we're going to take the cube root of this first house. The cube root of negative 64 is negative 4. For my x's, 9 divided by 3 is 3, so we bring out an x cubed. And for y, 21 divided by 3 is 7. So all of that came out of our radical. And our non-perfect part was the cube root of positive 1x. That was leaving our radicand positive, which it needed to be, and we took that negative out with the 64. Okay, on 14, we have the cube root of negative 81 p squared q to the 12th. So 81 is not a perfect cube. It's not divisible by 125 or 64, but it is divisible by 27. It is 27 times 3 if we test that on our calculator. So we're going to make our two houses, and it's going to be negative 27. The negative always goes in the first house, positive 3. Now p squared, 2 does not divide by 3, neither does 1 or 0. Now if your exponent is ever smaller than your index, the whole thing, we can't root any of it. Just automatically goes into your little reject house. Now Q12, 12 does divide by 3, so all of Q12 goes in the first house. Okay, first house is what we root. The cube root of negative 27 is negative 3. And then we do 12 divided by 3 is 4. So negative 3q to the 4th power came out, and we are left with the cube root of 3p squared as the remainder inside the radical. Okay, on number 15, now we're taking the 4th root. So that means our variables exponents need to be divisible by 4. And we would use our perfect fourths list. But on number 15, we do not have a number to 4th root, just variables and exponents. So I'm looking, 4 does divide by 4, but 17 doesn't. So I still need to make two houses because w to the 4th does divide evenly by 4. Notice, oh, I forgot to put those little 4s on the outside. That's important. We're going to put the whole thing in the first radical. Now 17 does not divide by 4. So I start subtracting one at a time because I want the biggest number possible to see what will divide by 4. 17 minus 1 is 16, which is divisible by 4. So we're going to keep 16 in the first house. Oh, and that's a v. Oops. V to the 16th. And we rejected one v to stay inside. So then we 4th root everything in the radical. So divide their exponents by 4 to let them out. 4 divided by 4 is 1. So we have one w on the outside. For v, 16 divided by 4 is 4. So 4 v's came out. Our little remainder part was the 4th root of 1v. Okay, 16, we have the 4th root of 48, m to the 8th, n cubed. Look at, I've got my perfect force list over here. 48's not on there, so I need to make two houses, two 4th root houses. Okay, don't forget that 4. It's a reminder to divide by 4 and not just square root. Now, can't be any of these numbers. They're all bigger than 48. So 48 divided by 16, or 48, yeah, is 3. So we're going to use this. 16 goes in the first house, 3 in the second. Now for my m's, 8 does divide by 4 evenly, so that whole thing goes in my first house. And cubed, okay, 3 is smaller than 4. We can't change that at all, so the whole thing goes in the second house. There's no part of that we can divide. And then we 4th root this. The 4th root of 16 is 2. And then 8 divided by 4 is also 2, so m squared. 2m squared came out, and we leave the 4th root of 3n cubed inside. Okay, on 17, we have the 4th root of 625c to the 23rd power d to the 11th. Now look at my number, 625 is on my list. So we already have the right number, but my exponents 23 and 11 do not divide by 4. So we'll still work with our two 4th root houses. Okay, so all of 625 goes in my first house because it's a perfect 4th. Now for my c's, 23 does not divide by 4. So I check 22, that's taking away 1. That does not. Neither does 21. And only when we get to 20 are we divisible by 4. That's the next biggest part. So I'm going to put 20 in my first house. And I had to kick out 3 to make that happen. So again, 20 plus 3 makes 23. I'm just rearranging them to what is divisible by 4, the biggest part. Now for my D's, okay, 11 does not divide by 4, neither does 10 or 9, not till we get to 8. So we're going to put D8 in the first house. And again, 11 minus 8 meant we're kicked out 3. And then we fourth root this whole first house. The fourth root of 625 is 5. We're dividing our exponents by 4 because it's a fourth root. So 20 divided by 4 is 5, c to the 5th power. 8 divided by 4, it gives me a d squared. Left over with a fourth root of c cubed, d cubed. And those exponents inside the radical, as part of your radicand, they should always be smaller than your index. Otherwise, you did not take out enough. Okay, last one. This one's a little bit different. We have the fourth root of a grouping. Okay, y plus 3 is all being raised to the 8th power. Because y plus 3 is in parentheses, we can kind of apply our rule in a different way. We can fourth root this. We would say 8 divided by 4 because of those parentheses, again, that are around y plus 3. So we would take out y plus 3 as a grouping, but now we have it to the 2nd power. 8 divided by 4 is 2. And then we are supposed to simplify. Y plus 3 squared means y plus 3 times its own self, y plus 3. So then we have to FOIL because that's what we do. Y times y is y squared plus 3y plus 3y again plus 3 times 3 is 9. Combine our like terms in the middle, and it's y squared plus 6y plus 9. That's our simplified answer that they're looking for. Okay, good luck on your assignment. You'll want to use your note card or your list of perfect squares, cubes, and fourths to help you solve these. Good luck.